So welcome everybody to the first of our Kickstarter Colloquia. This is intended to be a platform to feature the work by the many teams from TVS, STARS, Milky Way and Local Volume and the Solar System Science Collaborations that have been going on over the past, the stretch of the last year to prepare for a very wide range of science with LSST. So they're going to be short talks of representatives from each project featuring quite a wide range of our preparations. And there'll be time after each talk for your questions. As you've just noticed, these colloquia are going to be recorded, provided the speakers are happy with that, and I'll be posting the recordings on YouTube for the benefit of those who can't join us in person. So if you prefer not to be recorded, then just please keep your camera off. With that, I'd like to welcome our speakers. First of all, Meredith Rawls and Dino Bektesevic. Have I got that right? I apologize if I'm mispronouncing it.
Bektesevic.
Thank you very much. And also Fabio Ragosta, who will be telling us about their two projects to kick us off in this series. So first of all, I'd like to invite Meredith and Dino to tell us about Trailblazer.
Thank you. Let me get my screen share window to be the right chunk of my screen here. Always the fun part of doing your presentation. Dino, can you just do a quick mic check? When you unmuted a second ago, I didn't actually hear you at all. No. No. It'd be too easy if all of our hardware worked the first time.
Yeah, that.
Oh, there you are.
Now? Oh, okay.
Yeah, now you're good. Okay, no problem. All right. Well, thank you, Rachel, for organizing this and for coordinating the funding from the Kickstarter grant, because it has been a big help to us to be able to get this Trailblazer project off the ground. We're going to tell you a little bit about. Dino and I are going to split the time, so I'm going to start and tell you a little bit about the motivation of like why we needed to build this data repository for collecting satellite streaked images. And then Dino's going to talk a little bit about some of the more the nuts and bolts of how it works and kind of where we're headed next. We both are at University of Washington, I'll say, and I work for the Ribbon Project in data management. In a past life, I love doing stars, so my heart is with the TVS group, even though my actual hours tend to be on the software side, and then I'm dealing with satellites in my copious spare time. And Dino is I guess, am I allowed to say you're a PhD candidate? You're getting closer to being a PhD candidate at the University of Washington.
It's like kind of like fusion. It's just a decade away,
Fair enough. So the motivation for this project really has come about because the number of things orbiting space is increasing unsustainably and very rapidly. And low Earth orbit and Earth's orbital space environment in general is suddenly being populated with large numbers of these commercial satellites. If you take a look at this on the left here, we have a kind of a simulation of what the current, or I guess last year's satellite population looked like around Earth and low Earth orbit. And if you take at face value all of the applications that various companies have put in to say, yeah, we want to launch our own satellite constellation to do whatever thing, and you look forward to 2028, this is naively where you would get. Now, I don't think that necessarily every single one of these is going to launch, but we're going to be seeing a lot more impacts in our ground-based observations as the population increases, even if it's not quite this severe. And this shows up here too in this graph. This is from a recent Nature perspective that I co-authored. And it shows, in this blue line in particular, is the one that freaks me out at night. And it, because satellites have been increasing over time, and like debris is like a whole separate conversation that we are not going to have today. Oh, you're welcome to ask about it. And but this active line, really in the last 3 years, this is Starlink and OneWeb, just beginning to launch just oodles of satellites. And this is a trend that it seems to be continuing as best we can tell. So what this really looks like is you get streaks in your images. We'll show some more examples of these later, but this is one where there are actually a bunch of streaks in this particular image, one bright one and some fainter ones as well, when they were kind of all clumped together and going along. And the satellites leave streaks because they are orbiting really fast relative to your exposure time. You're trying to track the stars, and then it's like, here goes a bright thing. They reflect sunlight. So thankfully, they're not like shining lasers at us at the moment. It's all just reflection. But it's can be very bright reflection, depending on the exact physical properties of the surfaces. And these are most visible near twilight because they're not yet in Earth's shadow. So if you're trying to do any kind of twilight science that, like looking for things in the solar system, for example, then your science is going to be the most heavily impacted. But some satellites are visible all night long. So you can't just, even if your science allows you to just wait till midnight to take your observations, that is not a guarantee of 0 satellite streaks in your data. And the impacts here are worse for large, wide field, ground-based facilities, which might sound like everyone's favorite telescope. I'll talk about that more in a second. And there's also this issue where the satellites, they don't just magically appear in orbit, right? They have to get there, and then after their nominal life is done, they have to deorbit again. And those two phases, when they're launching and going up to their main orbit, and when they're done and they're burning up, are two of the brightest phases of their life cycle. And if you're maintaining a large population of satellites at all these different orbital altitudes, although most of the Starlinks are really this blue peak at 550 kilometers altitude. If you're trying to maintain this population, then you're going to be constantly launching and deorbiting, which is a problem. So this is another way to visualize the distribution of stuff. The y-axis here is arbitrary, just so you can kind of see it smooshed out. And you can see the Starlinks are here. There's a whole bunch of stuff out here as well. And the OneWebs are actually out here at around 1200. There's not as many of them, but they're out there. So you may have gathered, the reason this matters for Rubin is the same features that make Rubin amazing for discovery, right? It's wide field of view, its sensitivity to faint things, the fact that it's going to discover all these changing things over the course of the night are the same features that make it vulnerable to bright low Earth orbit satellites. So this is a little simulation that kind of shows how that works. It actually is a couple years old. It uses the satellite population from July 2020, so there were fewer then. But in evening twilight, shortly after sunset, all of these little existing satellites are going to be zipping across the sky. Some of them aren't as bright, right? Some of them are fainter. Maybe not going to mess with you as much, but some of the ones that are showing up more red are pretty bright, just depending on their reflective properties and where they happen to be relative to the sun angle and all that. You wait to the middle of the night, it's not as bad, but like I said before, they're not entirely gone. So, you might get unlucky. And then as the night wraps up, you start getting a whole bunch showing up on the eastern horizon, kind of preceding sunrise. So that is kind of what our nights are going to look like once Rubin comes online in a couple of years. So when I show people this, they like to say, okay, well, that is potentially terrifying, but what are the actual science impacts, right? Like, you could freak out about streaks, but like, what are the science impacts? And the short answer is that we don't have a very good handle on this yet because it's such a new problem. And this is one thing, spoiler, that we're building the Trailblazer repository to try to answer some of those questions by collecting the data that we need. But there was a study earlier this year that used Zwicky transient facility data, which is like almost a mini Rubin, right, in California at Palomar. And they took a look and they found that, yeah, indeed, they saw a bunch more Starlinks between January 2020 and September 2021. Surprise, population increased. They saw more streaks in their images. Like, indeed, they're looking at the sky. And again, so if we remember this plot from earlier, it was interesting because one of their conclusions was actually that the impact to their science was not yet significant, because mostly what they're doing is looking for like supernovae and transients and stuff. But if you remember that this like increase here really just corresponds to the beginning of this kind of unsustainable uptick, I think maybe the situation is a little different. And it's I can't predict the future. I can't guarantee that it's going to ruin everything. Hope it doesn't. But the fact that they're not seeing any science impacts yet is both a function of the fact that it's a smaller telescope and they're doing mostly a supernova detection type science, and that this is just the beginning of the kind of this new era in orbital space. So jury's out on exactly how this will shake down. However, to kind of study this issue and get a better handle on it and start to mitigate it from all these different angles, we were able to form a new IAU center for dealing with satellites. That's not the official name. The official name is the International Astronomical Union Center for the Protection of the Dark and Quiet Sky from Satellite Constellation Interference, or IAU CPS for short, because everyone loves a good acronym. We have a very shiny website I encourage you to check out. And there are 4 kind of main hubs within this this organization. And there's one that's focused on observations and data analysis that I'm co-chairing. And then there's also a policy hub, an industry and tech hub for interfacing with satellite operators, and a community engagement hub for trying to broaden the stakeholders that we bring to the table, because turns out this is not just a problem for satellite operators and astronomers. It's a problem for all night sky users, if you will. And that's important to keep in mind. But for the purposes of this talk, the work that we've been doing kind of falls under the umbrella of this Sat Hub concept, which is, it's brand new, so we're not solving all the problems yet. But the idea here is to be kind of one place to go to coordinate all of the efforts for observing satellites, for collecting the data, for analyzing the data, for teaching people how to do this. Oh, there's a satellite streak in my image, like what should I do? Like this is the resource to go to get that question answered. And that falls under kind of 5 subcategories, if you will. And the thing that we are working on is specifically in the astronomical data repositories kind of camp of SatHub, if you will. So our goal with building this Trailblazer that Dino's going to tell you about in a second is to collect and share data affected by satellites, because this can help quantify and ultimately mitigate the problems. If we don't have like examples in real time of what's happening in images, then we're just guessing, because it's really hard to model exactly how satellite streaks are going to appear. They're the opposite of spherical cows. They are not black bodies. They move, they rotate. It's awful. It's the atmosphere. They get drag. They don't show up where you expect them to. It's a really fun time. And the SatCon 2 report that I co-authored last year after a wonderful workshop that Dino and I both went to, it outlined a strong need for astronomical data repositories like this. So we were like, okay, let's start with a low-hanging fruit, if you will. Let's make a tool that can collect telescope FITS files that are known to have satellite streaks that have a valid WCS. And let's just like start a pile of them so that we can enable studies of how the satellite population is changing and what we might do about that. So that's what we're building, or what we have built. It's a free public open source website for collecting these images. You can check it out. We have a real website, it exists. And it also aims to bring attention to the problem in an accessible manner by having a kind of a landing page gallery at the top, if you will. So with that, I'm going to hand it over to Dino to tell you a little bit more of the specifics of what we've done.
Thanks a lot, Meredith. More concrete terms, we aim to collect this image data from users by having them upload to the website. We try to make this process as non-intrusive as possible, which means uploading compressed archives or linking to external existing data centers. It also means supporting programmatic upload, because in the long run, right, nobody really wants to upload a large number of images by hand via browser portal. But we of course recognize also that just hosting the data by itself is somewhat useless, especially because we aim to cover both the professional astronomers as well as non-professional astronomer community that's just looking for some data information material to educate and spread awareness about what we perceive as being a problem. So we expect our data to have a large spread in quality and availability of its metadata. So we want to help our users to eventually zero in on the kind of quality and data sources they want. So we need to make that data searchable. We focus basically only on the basic information of, who took the image, when did they take it, from where did they take it, with what instrument, what part of the sky. And if you can't get at least this bit of additional, this bit of metadata, we wouldn't be accepting their upload into our collection. We, of course, collect more metadata than just the main questions, as you'll see in a minute again, because we don't want to pigeonhole ourselves into collecting too little of it, but we would have to require at least the basic questions to be answered. I will note that the information we do collect has a little bit more of a general definition than what you might be used to if you, let's say, work a lot with Verisi Rubin science pipelines. But the goal of the data we collect is the metadata we extract is really all about allowing users to filter for the data they want. Of course, we want to enable them to do this from scripts, from Python scripts, Jupyter notebooks. So programmatic access to this metadata and filtering capabilities also needs to be there. So usually, that's sorted out with a REST API. You make a request from Python, you get back a dictionary. We feel like that would be a requirement for us because it's just way better than downloading a bunch of CSV files. Of course, it shouldn't stand in the way of ease of use, especially since we're catering to non-astronomy communities and individuals as well. So all of that needs to have a web-based access and an interface. Whether or not we can achieve full parity in features through the web-based interface kind of remains still to be seen. But we believe that we can get close at least, right? For the rest of the slides here today, I just kind of will want to run through the kind of stuff we have already from these requirements and where we got, and then hopefully I'll end up on where we want to get. If any of that is interesting to you, do come and get in touch via the GitHub issues or just pop us an email. So if you can jump to the next slide. I just want to give you an overview of the pipeline. So basically, user would upload some FITS images through the web portal or a REST API request. The processor would take that upload and then figure out what it needs to do with it. If it's an archive, it needs to unpack it. If it's a list of ID of an external data center, it needs to fetch the metadata or fetch the FITS file. But whatever it is, it eventually will boil down to something that represents a single extension FITS file or a multi-extension FITS file. These would process the metadata and the images to create, quote unquote, the standardized results we talked about. If you remember the 5-question who, when, with what, etc. So we would keep only the full bullet points, or we would require really only the full bullet points, like the time of the exposure, the location, the WCS, and we would collect more than that. But they don't have to exist for all of the data that is being processed, right? Other than the metadata that we extract and then store in a database that has a public access, we store the raw data as is. We also aim to create, an easy thumbnail preview, some eye candy for publications and further education and bring awareness to the issue, right? So naturally, sometimes, if you can go back a little bit, of course, the instruments can be, quite specific, have a design, that's very different from others, requires specialty processing, as you'll show in a minute, as well. And we enable that on a class-based approach where anybody can come in, write a small class that overrides any kind of default behavior we have coded up in our pipeline so far, right? The problem also doesn't lie solely in just the instrumentation being different. Sometimes even the different pipelines can produce different looking results from the same input data. And I'll show that later. So if you can jump to the next slide. Yeah, thank you. This is like what it looks like when a user contributes specialized, in this case, a header standardization class, right? It has, this particular one was added by an undergrad we worked in the previous quarter, and it just basically consists of the method, can standardize, with just checks on specific keys in the header, says, oh yes, I do recognize this file, I can process this, and then provides the override for standardization of the metadata from the header. In this case, geolon, geolat is not exactly standard, FITS header file keys. So that's pretty much all it takes. We support about a dozen instruments. So the big ones we kind of cover using the Rubin's Astro metadata translator. We have 5 or 6 specific overrides, mostly contributed by undergrads and grads from different universities. And then we have some generic classes that try to be as nice as possible and get as much data through as possible, even going as far as solving for some of them using astrometry.net. But of course, there's always something that can fail. If you got a file and you try to upload it and it failed, I mean, just get in touch. Contributing is easy. And these problems tend to just really boil down to translating header keys most of the time. So if you jump forward, once you did your upload and stuff, these images end up in our gallery. Image sizes in the gallery, you gotta keep this in mind. They're greatly reduced from the original resolution, so they're not always necessarily representative of the actual image. There's histogram manipulation, equalization that happens. So if you have a really thin line, they can disappear from the image. So just keep that in mind. So some of them look empty, but they're actually not. If you click on any of the small previews in the gallery, you'll get one big image like the one on the right alongside with its data. There'll be a button on the bottom where you can click and download it, including in the future supplemental information like detected lines and their coordinates in the pixel space, et cetera, et cetera. And here's the two images on the left that on the right, I apologize, that I've shown in big are the same image actually. The top left is one of the CCD frames from the bottom right image. The only difference is, like I mentioned before, that one was processed by Rubin science pipelines, the other one was processed by the community pipelines, but it's the same DECAM image from the same processing pipelines. So this is the kind of things, the framework for sorting this out, we kind of can provide if people are willing to contribute translation, let's say non-standard header keywords in cases where it fails. You can go to the next slide. This is just a more eye candy, a couple more examples of kind of images we collected with Trailblazer. In these cases, they're mostly from 0.5 meter to 1.5 meter telescopes from around the world. We have about 30 gigabytes of similar data. We have about 30,000 or so data, dating all the way.
Pagine, mannaggia la miseria.
Hi, everybody. Could you, if you're not actually speaking, please mute your microphone. Thank you.
Dating all the way back to SDSS, we got a couple of very recent DECAM type images, but of course, we're always working on getting our data set more filled. So if you want to contribute, please do. You can jump to the next slide. If you do, this is kind of the upload page and what it'll look like. It's a nice little drag and drop multi-file interface. You can add, remove files dynamically before you press the upload button. You can upload tar files and tar BZ2 files. After the uploading, you'll be redirected to the processing report page shown on the right. You can see which one failed, which one didn't fail. You can report them, open an issue on GitHub. At the moment, we don't supply the logs, unfortunately, but we do have the logs. We're working on that, so you get to see why it failed, maybe even fix the issue on your end before resubmitting. And of course, once they're uploaded, they'll appear in the gallery. Their metadata will also become available in the query app. If you go to the next slide, please, which kind of looks like this. This is at least the front end. It's not fantastically powerful on the front end for now, and probably the app that has the least work put into it in terms of work hours so far, but it will help you get kind of a quick insight into the kind of data we have and showcase some of the abilities of the querying we have. Like if you run the empty query, you'll get all of the results at the moment. We're working on getting them paginated, so you'll be able to download them as CSV file or something. There's querying by sky region, observatory location, date range, and then all of the individual keys and any combination between. If you jump forward, this is really what powers this query machine. It's the Restful API that underpins it. This, I might dare say, is actually pretty good. For those that are not as familiar, the REST API kind of just allows you to make programmatic requests to our service and then get back a response in form of HTTP request or a JSON response or YAML response, which is nice because they're easy, they're readily converted to lists and dictionaries in Python. So it's really easy to work with them. The slide, the kind of examples I put up is if you query the query metadata, so if you just copy that bit and paste it after Trailblazer direct dev, you'll get basically all of the results back. If you want a particular instrument, you can add in decam. After a question mark, we support case insensitive searches. We support fuzzy matching, like does it contain a part of the string, etc. We support querying on WCS information and then returning individual fields from metadata itself and any combination in between. We support the last query is showcasing a rectangle selection on the sky, the results of which are kind of shown on this little screenshot on the right. So it's like a list of all of the results that match the given red extension declination alongside with the WCSs, et cetera, et cetera. Right? So if anybody's interested, play around a bit, give us some feedback. We're always looking for upgrades and how to make this better. It is kind of unfortunate that there's not a full-on tutorial at the moment, but we're working on it. It's kind of funny how much time can be wasted and spent doing these things. If you jump to the next slide, right, as I was saying, improving services is definitely the main focus at the moment. This summer, with the help of eScience Institute, we ran a 10-week mixed graduate and undergraduate summer school. We took some of the data we had for Trailblazer, and then with them, over the 10 weeks, we developed a line detection pipeline that we called SAT metrics. It's also written in Python. It's also based on very generic data processing approaches and computer vision algorithms, which is nice because it tolerates a wide range of data sources, different baselines, different noise levels. It produces really robust detections, even on multi-streaked images, and it gets rid of double detections pretty easily. It's not the cleanest code ever at the moment, and it's not quite, integrated. There's still quite a bit of work to integrate it with Trailblazer, but we are working on it. We are getting there. Adding the code, won't just let us to check if the uploaded image actually has a line that we can detect, but it'll provide with the cutouts like the one shown on the bottom, with measurements of the cutouts, and in some cases we're hoping even calibrated measurements in terms of magnitudes. But in general, that's kind of difficult to do because the problem is that the exposure of the image is not the exposure of the trail, which tends to be, a fraction of a second that it took for that satellite to fly through your field of view. So figuring out how to calibrate these measurements is kind of tricky because you have to figure out the angular velocity of the satellite in your image, which requires other services that are not 100% yet up. But hey, happy to get anybody on board if they want to pursue this further. I think the other to-do stuff is also on the next slide. Stuff like making the upload, for example, which isn't quite programmatically done well yet, then integrating the external data center APIs, then getting our REST API into something like AstroQuery that people are comfortably using, integrating the SAT metric package like I just talked about in the last slide, many front-end website improvements. It turns out it's kind of difficult. It's really difficult. I'm not that great at it. Bugs seem to be endless. It's a very dynamic system. Browsers change, and to be supportive of multiple instruments, to be to have responsive HTML, it just turns out to be a lot of work. Couple of things, that can be done also, stuff like adding citation. At the moment, you might have noticed we require people to sign off their rights to the images. because citations are difficult, but adding a way for the user to provide per image basis citation that others can use would be really nice. Adding something like notes in the metadata to even further help users to set apart their data and make it searchable like that. This would all be very welcome. Of course, just because it's missing doesn't make really Trailblazer unusable right now. It might be clunky, but if you do have data, even if you can't upload it because it fails or it's too much, get in touch with us. We'll be happy to take it off your hands, make a copy, keep it around until we get Trailblazer to a point where it can digest something like that, and then we would be more than happy to host it. So yeah, I think that's a good point to end on. I'm not sure what our time is. Point being, get in touch. If you have suggestions, tell us. If you have improvements, tell us. If you don't find something acceptable or doesn't work, tell us. I think gallery at the moment might be still a little bit broken, but there is already a fix for that. It just hasn't been deployed yet, and so on and so on. I don't want to. I feel like I'm starting to run in circles a little bit. Yeah, thank you very much for listening.
Thank you both, Meredith and Dino. That was an excellent talk about a most terrifying subject, quite frankly. So thank you very much. Does anyone else have any questions?
Yes, of course we do.
Excellent.
Are you both in touch with the DM and the scheduling whatever a committee is, in a sense that you can avoid the hard cases?
Yeah, that's an excellent question. So we didn't have room to add a slide on this, but another summer project that I helped lead was to work with a student to investigate if Rubin could dodge satellites and if that would be worthwhile or not. And the short answer is yes, we can dodge satellites, and we can add that to the scheduler, and it can work. But in practice, we waste tons of time slewing around. And you lose a lot of exposures and survey depth right off the bat. So unless the satellites are like way more numerous and way more bright than they are right now, which is possible, that we could get into that regime. But at the moment, it's basically not worth it. But that doesn't directly connect to the project that we did with this, so I didn't go into it. But yeah, there are lots of potential connections.
No, I'm
here.
looking a little bit further.
Sure.
In a sense, whether we are going to be able to avoid the funny streaks.
Yeah, no, there's going to be streaks in Rubin data, is the short of it. Yeah.
And the next question is basically what you're going to do with the remnants of satellites, which are going to, unless we know all of them, which are going to do the mess occasionally, especially if they are a little bit further away.
Yeah, there's no plan that we know of that can mitigate their impact at the moment. And for a project like Rubin, it's okay because they're on the sky for so long. So in total percentage of pixels, they will say something like it's not worth it. But also this is with the current trends, which can change either which way. The best solution people at the moment have is just masking all of the pixels that have been impacted, whether from satellites, meteors, or trash. Luckily, trash seems to be very small, so it doesn't really show up that well. Does that answer your question?
With the satellites or whatever, especially if they are remnants of satellites, it can be a little bit tricky, if I understand correctly.
That is true. There are some instances where like debris can cause glints is a concern that people definitely have, including myself. Where even if it's a small piece of something and not an active satellite, it could suddenly show up as like a bright glint on either periodic or quasi-periodic or not. And this is the kind of thing that we hope that we will collect in Trailblazer, like kind of as a, before Rubin is 100% up and running, so that we can get a handle on what that looks like in other telescopes and prepare a little better.
Yeah, and get some statistics on how often do we expect that to happen, because it is surprisingly difficult.
I just hope they are not going to show up in alerts.
Yeah, me too. Stay tuned.
I think like the bigger issue is if they show up in the code templates, no?
It depends on what your science is.
Fair enough.
I see a question from Kostya and then from Will.
Hello. Thank you so much for your presentation. So I have a question related to how large is the scope of your database. So for example, we have some examples of high orbit satellites observed by ZTF founded in data releases. So it is not our data, but in SNET team, we just founded these examples and we have some collection. So do you need something like this, or are you targeted only to have these low orbit long trials? Thank you.
I mean, I would say that the primary goal is to get a handle on the increasing low Earth orbit commercial satellite population, but that we would not reject data that happen to be other things as well that could potentially have an impact. Yeah. Did you have anything to add?
Absolutely. No, absolutely. If you have such information, definitely share it with us. I think a lot of measurements and processing we can do in such a general data set will lead to rather larger errors on the measurement, and our plan is to hide behind statistics for that. So the more instruments we have, the more images of stuff we have, the better. So definitely we would be interested even in large high orbit satellites as well.
Well, what is your communication with DM and the scheduling community?
Well, I'm on the data management team, so that's something.
But yeah, like Meredith won't brag, but that much. But we did have a whole summer project for a student on RU grant that worked with Peter Joachim to simulate impacts of currently announced future satellite constellations. So I would say pretty good.
Yeah, I'm working on this on a lot of different angles. Trailblazer is one recent piece, but happy to chat more later if you have more questions about the general big picture for Rubin.
I think one more question from Will, and then we will move on to our next speaker. Go ahead, Will.
Thanks, Rach. Yeah, great talk. That was sobering and very interesting. Do we know yet are there predictions yet for what the impact of satellite constellations will be on the near-Earth object key science goal of Rubin? Are we in a territory yet where actually the main science is being compromised? Do we know that already?
That is actively being studied. Siegfried Egel is leading a study on that right now, and he gave me a slide that is not in this presentation, but that I shared at the PCW, that I believe that something like they need, I'm going to get the numbers wrong, but they need something like 6 observations over 4 days. Again, the numbers are wrong, to successfully detect an NEO. And now they're taking into account like what is the likelihood of satellite streaks affecting like some fraction of that to make some kind of prediction. But that is not yet out. I was just getting in touch with Siegfried if you want the latest on that, because it's absolutely a concern, but quantifying it is a lot of work.
Yeah, no, I'm sure it is. Well, I appreciate the clarification. Do we think that will be known before first light?
That's the hope, but the satellite population is continuously changing. So, right, you put out something being like, okay, given what's up there right now, like this is the impact, but then suddenly 5 more things are approved to launch and it's a whole new ballgame. So it's really just a challenge.
Just extrapolate a power law or something like that.
Yeah, but then also like the new ones might be surprisingly bright, right? Like SpaceX didn't expect their satellites to be this bright when they started launching them. Everyone was surprised. So that's heartening.
So I have done the check.
Great point. Yeah,
looking for the solar system objects, you still only lose a few % of pixels, even if there's a really big mega constellation and you do a twilight survey. it's still on par with what you lose from bright star streaks.
That's true. It's not like you're probably not going to lose like the whole image or anything like that. But if it's statistically, how often do you get unlucky? How often does it go over the thing you wouldn't have discovered otherwise?
Yeah, but it's on par with chip gaps and other streaks. So it's a few percent, but definitely not a killer.
Okay. Well, thank you all.
Yes, thank you, Meredith and Dino, for kicking off this series with such an important and frightening topic.
Can I add that I just want to elevate that Meredith is the single most relevant specialist on what's happening with the satellites in Rubin. So her connection with the DM is not just as a member of DM, but she is the single most knowledgeable person about this problem in Rubin, for sure.
Oh, thank you, Fed. You're wonderful.
Quite right.
I'll also take a moment to let everyone here know that I actually am going to be on parental leave from November through about March. So you'll get my autoresponder if you're freaking out about satellites in that time frame. But otherwise, yes, I'm happy to help you.
Congratulations.
Thank you.
Congratulations. Okay, everybody. Now I would like to welcome Fabio Ragosta, who is going to speak on a topic of a new topic of great interest to a lot of people in LSST. He's going to tell us about what LSST is going to detect with Kilonovae. Fabio.
Hello, everybody. After this amazing talk, I hope I would be at the level of the previous speaker. But let me share this screen and start my talk. Can you all see the screen?
Yep, we can see your screen.
Presentation. Okay. So first of all, I want to thank all the people that worked for this Kickstarter, and above everybody, you, Rachel, and also Sylvia and Igor that involved me and Thomas for this project on the analysis of detection and science part of Kilonovae with LSST. So this project has two papers that are quite ready. Let's say there are drafts, but one is basically focused on the observational part. Let's say how many, what is the fraction of the kilonovae that we were able to detect, and Thomas Omada will speak about this. I actually don't know when. And then the project, the mini project I'm working on for about the ability that we will have with the LSST to actually extract reliable information from the light curves, Kilonova light curves. So I told a lot of times the word kilonovae, but I did not explain what they are. They are known as the electromagnetic counterpart of binary compact object merger, but this merging does not give rise just to this electromagnetic counterpart, but it gives rise to a bunch of messengers from time scales from seconds to months, years, and we should be able to detect all the messengers, to gather informations, to be able to describe what is actually happening, what are the inside of the mechanisms that produces all the different phenomena. And this is the multi-messengers framework in which this project is moving its steps. But the problem of detecting this electromagnetic counterpart is not just the time scales, but also the localization, because we can use one of the different messengers to localize the source and then try to detect it. But when we use, for instance, the gravitational waves, we have like enormous regions that up to now are hard to survey, except for the lucky case of GW17 or 817 that, as you can see from this sky map, has a very small region with respect to the others that was easier to survey, and that allow us to have all that all the informations about the multi-wavelength, multi-wavelength radiation from the source, and that's what we are like to do: gather all the information possible. But when we face the electromagnetic part of the merging of the compact object binary merging, what we are dealing with. So we basically are dealing with light curves that fade very fast and also have a very fast evolution in colors. Very fast with respect to all the explosive transients that we know. We can see here an image from a work of Andreoni et collaborator, where they compare the evolution of the supernovae light curves with the only light curves known up to now from the counterpart of GW170817. And again, from Andreoni et collaborator, we have a first hint of what we will do with respect the detection of the kilonovae using LSST data. They simulate light curves templates of binary neutron stars and neutron star black holes merger, and they try to filter the light curves with respect to one or more selection criteria to see how many kilonovae we can detect, how deep we can go. Doing this first simple filter of having just two detection above some signal to noise rate threshold, they see that using the baseline of all the different rolling cadences, we can reach like 1,400 megaparsec. But just with two detection, we may not be able to have all the information needed to do all the science on the kilonova that we did with the first lucky case. So when we apply a more sophisticated filtering, we see that we lose a huge number of kilonovae. Of course, these numbers are just not actual numbers, but they are related to the 500,000 kilonovae that were injected in their simulation. So we, in a certain way, replicated the work that they did in that paper, and but with another scope. With the main reason, the main question, that drive this project is what will be the precision that we will have on the models parameters when we will fit the light curves that we will have from the LSST data, and are they enough with an uncertainty small enough to allow us to draw some conclusion on the physics. So the idea behind we produce starting from this question is to set actually a model of reference, and we used the Metzger et collaborator 2017. That is a really, let's say, quote, a simple toy model that use just 3 parameters: the ejecta mass, the velocity mass, and the opacity, to simulate the light course from Kilonovae. So we draw the values from the from prior distributions from these parameters. We use this software that, if you're interested, I will talk about in more deeply fashion. That is called NMMA, that stands for Nuclear Multi-Messenger Astrophysics. And we produce light curves that then we injected in the math framework to have the LSST observed light curves from the kilonova source. Then, because NMMA allow to also fit the observed light curves, we use NMMA to infer the parameters we injected at the first step of our workflow. With the aim to produce a distribution of uncertainties. So the project is not yet that step, but we are working to do that last step. We did all the simulations, and we also have produced the LSST observed light curves. This is just a stamp of the GitHub of this software that was developed by Kathleen and collaborator, and this is just the flowchart at the bottom of the slide is just some connection to see what the software is capable of. So it allows you to simulate light curves from models, from theoretical models, and also allow you also to use observed data from which you can extract actually the models using some processes or dimensionality reduction methods. And again, as I said before, it allows also to analyze data using different Bayesian samplers. Sorry. So let's give a look to what we had. This is a plot that show in a fixed region of the footprint using the baseline, the version 2.0 baseline. The templates of the Kilonovae produced in 3 different periods along the 10 years. As you can, and also at very in 3 different distances. So as you can see, going farther in distance prevent to populate late time part of the light curves. And sorry, one thing I did not tell you, that the dot point are color coded with respect to the filters, and the triangle has the same color coding of the dot, but they represent the non-detections. As you can see, there are periods of the survey in which, given a fixed region, we do not have always the same filter coverage, and these prevent us to have enough filters to do a more informative fit after. And these impact will of course impact the precision to which we will know the model parameters. And to describe what I just said, I I produced this, not so easy to read plot, so I'm sorry about it. But the different columns of this plot show from left to the right the peak magnitude of the light course, of the observed light course, the difference between the explosion time and the peak magnitude epoch, and then the difference between the explosion time and the last detection we have. As for going to the fourth and the fifth column, the rise rate and the fall rate. Of course, the template light curves are the same. So the differences between this distribution is to be related to the observing strategy. And of course, sorry for the of course, is not so obvious. Also the difference between the distribution going from closer to farther distances are also related to the fact that we do not populate late time part of the light curves, because going deeper we miss a lot of detection. But the survey strategy is not the only thing that can impact the uncertainty on the parameter of the model parameters, but also the filter, the Bayesian sampler we use. So we try to see what is the impact from the sampler on the detection cadences, number of filters, and peak magnitudes. So fixing, for instance, fixing the number of filters and the peak magnitude, we first change the detection's cadence. This means that we change the time distance between two adjacent detections, and this impacts the number of points on the light course. As for the peak magnitude, we fix the detection cadence and the number of filter, and changing the peak magnitude, we simulate having a fainter and fainter Kilonovae. And for the number of filter, we just change the number of the numbers, the information weight to produce to perform the fit. And so we developed these plots to see how the performance is impacted from the number of detection of light courses. As you can see, going from sorry, there is an error in this arrow. Apologies. The x-axis go from higher number of detection to lower number of detection. So the axis going from higher to small to lower points on the light curves, and as in a certain sense expected, we have that the performance in the fitting is lower when we have lower points on the light course, and we apply the analysis applying having a different number of filters, having so and what we can see is that having more and more filters. Of course, here we are constrained to have from 1 to 5 or 6, no, actually 1 to 5 filters. And as you can see, the performances reach the higher plateau already when we use just 3 filters to perform the fit. And finally, we analyzed how change how the performance is impacted by changing the peak magnitude. There is this weird behavior in the going deeper. Sorry, in the fifth point, that you can see appear higher in the performance with respect to the general trend. So we analyzed what is going on with the sampler. So we look at the best one performance and the worst one, and we compare the two distribution with this weird performance case. And what we saw is that if we look at the ejecta mass distribution in the parameter space and the velocity mass distribution, we note that if the ejecta velocity region are almost uniformly surveyed by the sampler, the ejecta mass region, the ejecta mass direction is peaked when the performance is higher and is almost uniform when the performance is lower. So in this case, in this weird case, the ejecta mass direction is very broad, but the sampler was able to find like a peaked region, and that's why the performance in that case is better. So we, in a final stage, what we thought is if this is the behavior of the sampler, it can be related just to the sampler or to the model. So we analyzed the model, calculating the uncertainties for the two different from the ejecta mass and the velocity mass with respect the mass of the primary star in the binary system. And so we just this A value is a proxy of, let's say, the sensibility to which we can know the model parameter given different binary sources. So as you can see from this plot, when we look at the ejecta mass, there are changes due to there are changing in the uncertainties with respect to different binary merging scenarios. While looking at the ejecta velocity, the trend is almost flat, and this gives us reason to think that the behavior we saw in the fitting procedure is due to the model we used. So at last, as for the last slide, I just want to say that we started to think to use all these results we are gathering from this project also to see what we have to how we can use LSST data to constrain what will be the kilonova science in 04, 05, and also when the survey will finish and other gravitational wave detectors as Cosmic Explorer and the ICEN telescope will start their operation. This is just a slide to summarize everything I said. And just a note on the next steps, we will try to see how these uncertainties on the parameters will impact also the knowledge we can have on the equation of states of the neutron stars. So I want to thank you for listening to me with these pictures that that show the four of us in row last June, let's say. So with this, we all symbolically thank you for give us the opportunity to work on this topic. So thank you.
Thank you very much, Fabio. That was an excellent talk, and I'm so glad to see your work on this follow-up and how LSST can actually help narrow down these localization regions. I noticed how important the LSST TOOs are going to be to this subject, but I'm also aware that there's a lot of pressure on the LSST schedule as a whole, so it will probably do TOOs. I know that the team are looking into that, but it will probably do a limited number of them. So what's the plan for presumably the other alerts that LSST won't be able to follow?
So I think that if I get the question, I think that the synergies with the other facilities we can obviously help with this. I mean, whenever LSST cannot look at this, is not looking in a certain region, supposedly some others will do that. And so what we can think about is to use also LSST as a TO facility. I was thinking about the commissioning camp, for instance, if not the LSST telescope. But also, I think that mainly building more profound synergies with all the facilities, ground-based and space-based facilities, it will give, will benefit a lot to this project.
Absolutely, for sure, yes. Does anyone have any other questions?
And also, sorry, if I can comment
sure,
more.
Yeah, please.
Sorry, there is this work from Lynn Talk at PCW. She actually did some look into the the impact that TOs will have on the survey, and actually she provided a very interesting results that using the TOs images as survey as images of the survey, there is like a trade-off between what we lose giving a percentage of time to TOs and what we gather because we anyway cover with LSST a certain kind of region. And basically the science cases the science cases she looked into won't be so impacted by using for instance the 10% of time to or no, it was like 10 TOs per year or 50 TOs per year. Both cases won't impact too much science cases.
That's good to know.
Okay, my question is about multi-messenger or messenger. You did mention once or twice multi-messenger science. What is here about multi-messenger science? Because what it is basically optical science or whatever.
Yeah. In this project, we use we use it just the optical. Of course, you know, there is some subtleties in the logic of the project, because we are saying that we can actually localize the all the kilonovae we are observing, and this is not always true. So we are implicitly saying that we were able to localize the event from a GRB localization or from a gravitational waves trigger. So the multi-messenger side of this project is hidden from this in this assumption.
Okay. Never mind. Well, let's discuss that later on, because there are quite a few of polls, if I understood it.
Sorry, I missed your
Never
comment.
mind.
Possibly we can follow up on that question offline. I am consciously aware that we are close to time already, but thank you very much, Fabio. And thank you very much to all our speakers today for the first of this Kickstarter Colloquium. I think we're off to a tremendous start. And obviously you can find all of our speakers on the LSSTC Slack system if you have any follow-up questions you would like to ask them. And with that, I will let you know just to keep an eye on the Slack system for future announcements. This will be a colloquium series. We will be hearing from many more of our Kickstarter projects over the next couple of months. So do look out for future announcements of other colloquium. And with that, I will thank you all very much for your time. I'll see you next time.
Thanks, everybody.
Bye-bye now.
Thanks, bye.